that's fine. So as far as taking notes, if you want to go into Pearson and open up your textbook to the Chapter 13 review. Just load it up and show me. One of the things that I'm going to point out to you in Chapter 13 that you do not need to worry about doing, that if we had more time, I would probably teach you to do this, but given that we don't have a lot of time, I'm not going to, because you can get by without it. This whole idea of curve sketching, we're not going to do any curve sketching. So don't do any MyMathLab homework before next class period. Okay? Don't do any of it, because I'm really likely to condense it all down into just one homework section, which will save you a lot of time. And then I'll also put in just a review quiz for Chapter 13, but I'm going to do a review quiz of Chapter 13 and 14 together. So it'll be a condensed version of both quizzes. There's only 2 topics in Chapter 14 that we're going to cover, and I think they're in 2 different sections, but I'm going to cover the topic, not everything that's in that section. And the reason I'm going to do it that way is because I know these particular ideas that I'm going to give you, you'll have to know for the final exam. So I want you to see the kind of problem that you would have from Chapter 13 on the final exam, and the kind of problems that you would see from Chapter 14 on the final exam. So this is going to be a really, really directed lesson. I'm looking for a problem that you would not have the answer to, so it'll give you the best information. Okay, let's look at problem number 64, which is on page 749 of your textbook. Stop that. Okay, if you want to ask me questions about it after class, that's fine. Okay, so here's our problem. get this to where we can see both. So what we see here is, excuse me, it says in 2013, the price of gasoline in the United States spiked and then dropped. The average monthly price in cents per gallon of unleaded regular gasoline for 2013 can be approximated by this function, which is a cubic function. And this function is only valid for the interval 0 through 12, where 0 is January 2013, and then 12 would of course be December 2013. So this is only a function for 1 year of time. What they want us to do is they want us to determine the intervals on which the price was increasing, the intervals on which the price was decreasing, and then find any relative extrema. So we need to actually talk about what those three things mean. A function is increasing when, if you read the graph, it travels upward from left to right. Yes. Thank you. I forget to do that. Thank you. Is that better? Yeah. Okay, a function's increasing if you look at a picture of its graph. Now this is the common sense part of it. This is something you would know from any previous math course you took. A function's increasing if its slope is positive, basically, right? It travels uphill from left to right, so its slope is positive. What do you know about the connection between a derivative of a function and its slope? It's the same thing, okay? So a function is going to be increasing when its derivative is positive. And it's not hard to determine when its derivative is positive. You can plug in numbers and look at a table of values. You can actually graph the derivative and see where the derivative is above the x-axis. That tells you that it's positive. By the same idea, a function is decreasing when, if you read it from left to right, its graph travels downhill. In other words, when its slope is negative, which means that it is decreasing when the derivative is negative. Okay? Now, is there anything hard to understand about that? Does that make sense to everybody? Okay, my next question follows kind of after those two. What do you know happens between a function increasing and it decreasing? What has to happen when its slope changes from positive to negative? Say it again? Okay. What did you say? It has to plateau. It has to peak. Both of those are right. Okay? What happens, and I'm going to draw a real simple function here for you. What happens if this is my function What's the derivative here? Is it positive or negative? Okay, so it's greater than 0. What about the derivative over here? Negative. Then what happened where it plateaued? What would the value of the derivative be? That's right. It would be 0. What would we, if this was a profit function, would you care what that point was? Yeah, a lot. Why? That's where you maximize your profit. You don't want to go beyond that because you're starting to lose profit. You're still making profit, but your profit is not as high as it used to be. And on the way up, you're approaching your maximum profit. So this is a good place to be. You want a way to find that. Do you want to have to graph every time you find it? No. What you want to do is you want to find where the derivative is equal to 0. And that tells you where your maximum profit is, if this is a profit function. Okay? What if we talk about a cost function? That's right, you want to find the opposite. So if you have a cost function, and I'm just, using a really simple one, if you have this and this is a cost function, then the derivative is negative on this side because it's going downhill. The derivative is positive on this side because it's going uphill. But here's the point where you usually want to be. You want minimum cost, because hopefully minimum cost will at least not only minimize how much you're spending to make something, but hopefully it relates to that. Okay? Now, of course, you got that pesky revenue function in there between that may mess with a perfect correlation here, but most of the time you do want to do this as much as you can. So this is again where your derivative is going to be equal to 0, so that's going to be your minimum cost function. So now let's go back and look at the problem for the price of gasoline. The function that they give us, as we've already said, is a cubic function. Now there's the complete model for the function. The equation, of course, is the main thing we're interested in, but we need to keep in mind the context of the equation. So this is the price in cents per gallon of unleaded gasoline, unleaded regular gasoline, if we're going to be real technical. For 2013, at any time t, where t equals 0 is January 1, basically. Because that would be the beginning of 2013. And they want to know, when is the price increasing? Now, we could just graph that function. And we are going to graph that function. But the calculus says I can find the answer to the equation without graphing the function. And sometimes graphing the function is kind of a pain because, let's face it, finding a window for them sometimes is challenging. So since this is what, is it hard to take this derivative? Oh, this is an easy derivative to take. So P prime of t is equal to 3 times 0.1244 t to the second power minus 2 times 3.001 t plus 16.65. And this is so that's the change in the price of gasoline in cents per gallon and the rest of whatever that says, okay? We want to find when P prime is increasing, or when P prime is positive, actually. When is it positive? Well, 3 times 0.1244, get my calculator here. Well, I'm not going to put it there. We're just going to do some arithmetic first. We'll do the easy way. Is going to be 0.3732 t squared minus 6.002 t plus 16.65. We know that the derivative is positive on one side of where it's 0 and negative on the other side of where it's equal to 0. Numerically, without going to n deriv, even though we could use n deriv, but numerically, how would you find out where that function is equal to 0? Set it equal to 0. How do you solve that? Algebraically, how do you solve that? Quadratic equation. Right? Only in this case, the opposite of B is positive 6.002 because B is negative. So that's just an arithmetic problem.
Is it 11.168884?
Yeah.
I think there's just, I can't really read it all, but it looks like, is there just two on your sheet?
Yes. I'm sorry, I thought it was, you were talking about on the
I
calculator.
just didn't know if I couldn't see the same thing.
Okay. Yeah, thank you. But doing the arithmetic now. 7464. And we'll just call that 9. Why are we getting 2 answers? But shouldn't there only be, does that function, why would the derivative have a 0 in 2 places? Why are there 2 zeros? What's the derivative telling you?
It's got two.
Yeah. What do you know about what that function looks like? What does that function look like? An N shape? Yeah, it's a cubic function. So it's got a maximum and it's got a minimum. So it has 2 zeros. Okay, and that's possible. So what we know then is that this is the relative extrema. P of t is maximized at 12.51. Now here's the question. Did it hit its maximum if the function's only valid from 0 to 12? Did it even hit its maximum in that time interval? No. Or maybe that's a minimum. Who knows? That just tells you what the value of the derivative is. That's the x value. It says the derivative is 0. That might be where it bottomed out. It may have bottomed out after December 2013. So the other zero, and I'm just going to put a question mark there because we don't know if it's maximized or minimized. But P of T is also maximized or minimized at 3.56. Now this is after December. This is halfway through January of the next year. But this is a little better than halfway through March. How are we going to tell which one is a maximum and which one is a minimum? Because we know the function has both. How do we figure out which is which? Wouldn't you go back to here and plug them in and see which one gives the highest value and which one gives the lowest value?
We just look at which one's higher and which one's lower.
That's all you're really asking.
Yeah, without having to plug it in.
So, again, I'm just using arithmetic. I'm not using a lot of technology here. Since the original function is 0.1244, and the value of x we're looking at here is, let's look first at the 3.56, because I'm betting that's the maximum. Even though it seems kind of counterintuitive, you got to think about what you're actually looking at. So that's 3.56 cubed minus 3.001, again, times 3.56 squared plus 16.65 times 3.56 plus 348. And again, we're going into this equation right here. We're not really checking the other one yet because the price function is not really valid for anything bigger than 12. So we hit enter, and the answer comes out to be 374.85 cents. Remember, the price is in cents per gallon. So how much is that really? $3.75. Okay. So $3.75 per gallon. Now, in order to determine if this is indeed a maximum, all we really need to do then is say, okay, let's go a little bit less than 3.56. Like maybe 3. Because that would have been at the beginning of March. So at the beginning of March, it was 374. And then doing the same thing and going to 4, which is beginning of April. It was back to 374.5. So, let's go ahead and add the third decimal place there so that we can show that there really is a distinction. So at $3.56, the price was $3.758 per gallon. Whereas at the beginning of March, it was $3.743 per gallon. And at the beginning of April, it was $3.745 per gallon. So that clearly is a maximum. Do you agree? So other than taking the derivative, let me move the calculator out of the way for you, Katie, and maximize that. That better?
Yeah, it's better.
So I think we've answered the question that they asked us. But now let's try to put it in context. So from January 1, 2013 until about mid-March 2013, gas prices rose.
Can you read that, please?
Oh, sorry, thank you. That means the derivative was positive. And at this point, we knew that was when the derivative was negative. Okay? Now your question might be, well, how do they know that was the right function? You know, for the first time, I think this room actually is hot. We prop the door open at night because it's freezing. Somehow today it's managed to be hot. Let's just open them both. So really, this is the basic idea behind all of chapter 13. How can you find the maximum or the minimum of a function? You need to find its derivative, and then find out when the derivative is positive and when it's negative. Now there is another arithmetic trick, if you will, to finding out when it's positive and negative, but this is essentially what it is. Not everything is quite as easy to find its 0 point though. Sometimes we will have to graph the function and the derivative to figure out where they're positive and negative so that we know when the function's increasing and decreasing. Now, if you're wondering where on earth they would have come up with that function, the government keeps a database. And you can actually go into that database and find the gasoline prices for every single day of every single year as an average across the United States. And also go into individual states and find the price of gasoline every single day of every single year for each state. So the way they got that function, they gathered the data and they did regression on it. If you remember the first chapter, in chapter 11, I had you do a modeling problem where I gave you a table of data and told you to fit a function to it. When I have you do chapter 13 for your quiz or your test, that's what I'm going to give you. I'm going to give you a modeling problem and tell you, I'm either going to give you the data or I may have you go look the data up and tell you to fit a function to it and tell me when it is maximized, when it's minimized, when is it increasing, when is it decreasing, and why does anybody care? This is the why does anybody care. Okay? So looking through some of the rest of these, I don't think there's any modeling problems actually at the end of chapter 13, but I've got some. I think right now that's the only problem that I actually want to do with you. I'll look at some of the others later. Do you have any questions about how to do what we've just done? Because basically this is an overview of all of chapter 13. If you can work this problem, you know what you need to know from chapter 13. Okay, then let's go and try a similar function and talk about how we can find where the function is maximum, when it's at a minimum, when is it increasing, when is it decreasing. But this time we're going to need to do the problem when we don't have one that it's quite so easy to tell from the derivative. So let's go to problem number Let's go to problem number 31. Because we're going to use the calculator in problem number 31. It's going to be a lot of help to us. So, and this time, instead of actually doing any of this stuff by hand, even though we can, let's go and put the graph of the problem in y1. So y1 is equal to the quantity, whoops, keep forgetting I can't use parentheses on the keyboard, the quantity x times e to the x divided by x minus 1. Now, I'm not really interested in the values of that particular function, and I will graph it, but not right now. I want you to go to y2. And I want you to enter in deriv. And I want you to find the derivative of that function in y1. And the quickest way to do that, since we've already typed it in, is to say second vars, I'm sorry, not second vars, just vars, over to y vars, choose function, and choose y1, and put in x, comma, x. So we have the function, but we're not looking at the graph of the function. We have the derivative of the function in y2. We can do two things. We can either go look at the graph of the derivative, which is probably not going to be really helpful since we have no idea what kind of domain we would want to look at, or we can go look at the table. Only to look at the table, I want us to go and let it automatically populate that table. Okay? Now the one thing that we know about this function is that neither it nor its derivative is going to be defined when x is equal to 1. Does everybody realize why? What was the cardinal sin if we let x be 1? Be undefined. So that means if the function's not defined, the derivative isn't either. But we're going to go ahead and let it start at 0, and we're just going to go look, and it's going to increment by 1 to start with. So we're going to go to the table, and notice it's only showing you the value of the derivative, not the function. Okay? Now immediately you see that the value of the derivative at x equals 0 is -1. Now the numerical derivative is defined, but it's really close to 0. Because that's 2.72 times 10, I'm sorry, it's not either, it's really huge. Because that's 2.72 e to the 6th means you move the decimal 6 places to the right. So something funny went on at 1, and because that was a rational function, what went on at 1 was the function went up, and it came to the bottom and went out. Okay? It had an asymptote. But we can see that before 1, it was negative. But then suddenly it became positive again. So if I scroll backwards, I notice that the derivative is getting smaller and smaller and smaller. And it's approaching 0, but it's not 0. And then as I get larger and larger and larger, the derivative is growing. So for values that are greater than 1, the derivative is positive. For values that are less than 1, it's still positive. Wonder what that means about the function. So let's go back and look at a graph of the function, not the derivative, but of the function. And I may have chosen too big a window. We'll have to see. I did. I chose too big a window. Ah. That's pretty huge. Let's try to trim that down. Let's just go for 75,000. Okay, so here's your table. Sometimes a table helps you analyze better than the graph. It has an x-intercept and a y-intercept of 0, 0. It goes through the origin. But for negative values, it just approaches 0. So that's why we're not seeing anything happen when x is negative. We know it's undefined at x equals 1. But after it passes x equals 1, it grows really, really fast, which shouldn't be surprising because you have e to the x, which is an exponential function, and that's what they do. So if we look on a little bit smaller window, what you see is that the function keeps on going up and up and up and up and up. In fact, I can go over here to the window, and that's 24,473. So if I go up to 50,000 and just keep going up, so does the graph. And since there's not much happening back there, we'll let that go to 0. Does that function have a maximum? No. Is its derivative ever going to have a 0? No. The function itself has a 0. The derivative doesn't have one. It never actually reaches 0. The one place that it is a little bit funky is it says that the derivative is -1 at x equals 0. Well, that's for a different reason entirely. And the fact that the derivative is -1 doesn't really say anything to us at x equals 0. And the fact that it's giving you the value of 2.723 or 2.723 with all the zeros after it, well, it doesn't make any difference because the function itself is undefined there. So the value of the numerical derivative there is absolutely useless. It doesn't help you a bit. So how would you answer the question, find the locations and values of all relative maxima and minima for problem number 31? What would you say? It has no relative maxima or minima. It doesn't have a maximum value. It doesn't have a minimum value because its derivative is never going to be equal to 0. And you can actually show yourself that the derivative is never going to be equal to 0 . There goes your derivative. And if I even let it go below the x-axis so that you see it never crosses the x-axis, you can see that it's coming up close, but it's not crossing. And if I really narrow the window down, right there is where oops. Yeah, that is the graph, the derivative. So apparently the derivative does, whoops, have a zero because it looks like it has one right there. So if we go to trace, tell it we want to find the zero. There it comes. Says it has a zero at x equals 1.61. So if that's really a zero, then my function at that same value should reach a maximum. Now it's telling me there's no sign change. Now I know the reason that it didn't. It was because I actually tried to find the zero of the function itself. So let me get to the function itself, which get to the derivative, which is right there, and put in a left bound of 1 and a right bound of 2. And it says that the derivative does have a zero right there, but if I move back up to the function, what happened to the function at that point? What happened to the function at that point? No, the function's right there. This is the asymptote. Let me kind of narrow down our window for a minute. I'm actually going to turn off the derivative because we know where the zero for the derivative is. And it remembers that last x value, so I'm just going to tell it let x be x. Oh, I guess not. Okay, let's try again. It should have remembered it. This ought to be close. What do you notice happened to the function right there? So we talked about maximums. What happened to the function right there? maximum, what is it? And that's a minimum there. Is that really a minimum? No, because it went down to negative infinity before it got to 1. So did the derivative lie? No, it found what, for part of it, seemed to be a 0. So there is more to the story than I've told you so far. Okay? You do set your first derivative equal to 0 to find your extrema, maximums and minimums. But sometimes the derivative, when you find where it's equal to 0, it'll tell you the function has a maximum or a minimum, and in reality it doesn't. But there is another test that will tell you whether or not that was true, and it's something called the second derivative test. What you're doing is you're going to look for where basically in plain English, you're going to find the derivative of the first derivative. You're going to find the derivative of the derivative. And you're going to set it equal to 0, and if it tells you that that value is 0 somewhere, then that'll tell you the value of the function where the function has leveled out and there is no rate of change. In other words, it'll tell you if you've got an inflection point or if really the derivative was just lying. What this actually is an inflection point in the function. That's what that value actually is right there. It's an inflection point in the function. Because what happens is it's coming downhill really, really fast, and then it changes directions. Okay? This is also what will be referred to as a local minimum. It does hit a minimum, but not a minimum over the entire range of the function. It's called a local minimum. On this little small window, it reached a minimum value if I go from 1 to, let's say, 3. It did hit a minimum value. Now what I want you to do is look at the problems that you have and show me, and I'm actually going to try to help you with those this time.
This is recorded, right?
Yes.
Okay.
And I haven't unlocked these yet, so we're just going to look at them together. And then I'll unlock them after I've told you which ones you want to look at, because I'm not going to necessarily make you do them all. Can you answer that question? I'm not asking you to take any derivatives. You don't have an equation to take a derivative of. Can you answer the question based on what you see? So tell me, where is the function increasing? Well, it's actually increasing on 2 different intervals.
-1 up.
Okay, from -1 up to where? Where does it? It's like about 2. Okay, so on the interval from -1 to 2, it's increasing. And then again, it's increasing from 4 to positive infinity. Okay? Where is it decreasing? Negative infinity to -1, and from 2, which is where that peaks, starts going downhill until it gets to 4. So from 2 to 4.
Why would it be negative infinity just coming from the top?
Because it's coming from positive infinity on the y-axis, but it's coming from values that are negative infinity on the x-axis. So when you talk about where it's increasing and decreasing, you're talking about the x values where that happens. Okay? Given that that's a cubic and the one we just did was a cubic, do you think you can do that one without my help? Because I think that one I do want you to do for practice. You should be able to follow what I did in class today and do that. It's not in context, so there's no interpretation. All you need to do is tell me where that function is increasing and decreasing based on the values of the derivative. This one tells you to actually graph the function. And the function is 2x plus 4 raised to the power, and the power is a fraction, 2/5. Now, eventually we'll look at the derivative, but I'm going to leave it turned off right now. And I'm just going to have this, first I'm just going to zoom 6 just to get an idea of what it does. Now that shouldn't be a really huge, great surprise because that 2/5 power tells you that that's a fifth root of something. Okay? It's the fifth root of 2x plus 4 squared. And the fact that it's the fifth root of 2x plus 4 squared is what causes that. So looking, where is the function decreasing? You don't have to give me a number yet, but where is it decreasing? From, it looks like about -2. So it's coming from -2, from negative infinity up to -2, it appears to be decreasing. And then from about -2 up to positive infinity, it is increasing. Now I'm going to turn the derivative on. Now you can just barely see the derivative, but you can see it. What happened to the derivative where the function came to that little sharp point? What do you know about the derivative of a function that comes to a sharp point? It's not defined. There is no derivative when it comes to the sharp point. It looks to me like the derivative has an asymptote at that point. And that actually is true. Because if you take this derivative what happens is it doesn't really make any difference what value of x you put in here because you're going to square it. So this is defined for all values of x. And if you wanted to find out where that 0 was, all you have to do is set this part equal to 0. So at x equals -2, that was where your function had that sharp point because it touched the x-axis at that point. It actually had a value of 0 there because all you're doing is taking the fifth root of 0, and that's 0. But when you do its derivative, this is a chain rule problem. And 2 times 2/5 is 4/5 times 2x plus 4, but 2/5 minus 1 is -3/5. And this is one of the places where being able to do the algebra actually gives you some insight, because this says put this down in the denominator. So this doesn't give you much insight into why that thing has an asymptote. But this begins to give you that reason. Because what can you not have in the denominator? You can't have a 0. So if 2x plus 4 is equal to 0, which means x is equal to -2, just like it was on the function itself up here, this is undefined. Okay? So the derivative didn't exist. Now, it exists everywhere else except that. So all you have to look at after that then is go back to that graph or look at a table of values. So here's what happens. When the values are less than -2, the value of the derivative is negative, which tells you the function is decreasing. And when the values are greater than -2, you see the values are positive, which tells you the function is increasing. But I want you to notice what happened when you got to -2, because your calculator lied. It says that if you plug in -2 into the derivative, you get 0. No, you don't. You can't. Because if you plug in -2, the denominator of that derivative is undefined. Be careful of numerical differentiation. Most of the time it works. But the problem is it's a numerical process. It substitutes in numbers, and it does what you learned about in chapter 11. It looks for places and it'll substitute in this number, and then it'll move a little closer, and move a little closer, and move a little closer. And at some point, because it's just doing numerical approximations, it reaches a number that's small enough, it says, oh, well, that must be 0. And it just tells you it's 0, when in fact it's not. Okay? So you can't always trust your calculator. Be careful. Always have a backup method just in case. And looking at a graph is a good backup method, because the graph caught what the numerical derivative didn't. Okay? Where are you going to have a problem with that function? At x equals -2. I want you to do problem 2 and problem 4. I did 1 and 3 with you. You do problem 2 and problem 4 before I see you the next time and see how you do. Okay? 2 and 4. We did 3. We did 3 just now. We did that one. Problem 2 is just like the one that we did